Watauga County, North Carolina, 1879. While every neighbor rushed to get their cabin floors down before the next spring rain, Robert Dixon was on his hands and knees with a hand spade, digging a 6-inch trench completely around the interior of his new cabin, right against the log walls, 4 inches deep. His neighbor Samuel Hartley watched this peculiar spectacle and shook his head. They called it wasteful. They called him a fool. Standard frontier practice was simple. Set your sill logs on stone, chink the gaps with mud and moss, get your floorboards down fast. Dixon spent 2 full days digging that trench, lining it with river stones, connecting it to a drain pipe made from hollowed basswood. 16 hours of labor, his neighbors said, accomplished nothing. Then the wet years began. 1880 to 1882 brought 40% more rain than normal. Continuous spring flooding, summer storms that turned neighbors' cabins into soggy disasters. Samuel Hartley's sill logs started rotting. The Morrison place developed persistent puddles under the kitchen floor. The Miller family's north wall began to sag. But Dixon's cabin? Bone dry. His stone-lined trench carried away every drop of water that found its way inside, while his neighbors faced weeks of jacking up walls, replacing rotted sill logs, and rebuilding entire sections. What did this third-generation mountaineer understand about water and wood that his community dismissed as overthinking? If you value stories of practical wisdom that stood the test of time, make sure to subscribe. We've got more documented accounts worth remembering. Comment your city and state below. Spring had arrived early in Watauga County that year, and with it came the familiar urgency that gripped every settler preparing for another mountain winter. The snowmelt of 1879 created rushing creeks and soft ground, perfect conditions for the foundation work that would determine whether a family survived the coming cold months in comfort or misery. Along the ridgelines and in the hollows, the sound of axes and adzes echoed as men raced against time to complete their cabins before the first hard freeze. Robert Dixon had chosen his building site with the methodical care that marked everything he did, a gentle slope that would drain naturally, protected from the worst winter winds by a stand of mature chestnut trees. Close enough to the creek for water, but high enough to avoid spring floods. His foundation stones, quarried from the ridge above, and hauled down one at a time over the course of 2 months, sat perfectly level and properly spaced. The sill logs, carefully selected 18-inch white oak timbers, had been notched and fitted with the precision his German grandfather had taught him as a boy. But while his neighbors moved quickly to the next phase of construction, Dixon lingered over what most considered the simplest part of cabin building, installing the floor. Samuel Hartley had stopped by 3 times in the past week, each visit revealing his growing bewilderment at Dixon's approach to what should have been a straightforward task. Where other builders simply laid their floor joists across the sill logs and nailed down their puncheon boards in a matter of hours, Dixon seemed determined to complicate every step. The morning that would define their relationship began with Hartley arriving to find Dixon on his hands and knees inside the cabin, carefully measuring and marking a line 6 inches from the interior wall all the way around the perimeter. The hand spade beside him suggested an intention that seemed to defy all logic. Hartley had built more than 20 cabins in the county over the past 14 years, each one following the proven methods that had sheltered families successfully through countless mountain winters. The sight of a grown man preparing to dig inside his own house struck him as evidence of either madness or dangerous overthinking. "Robert, what in the Lord's name are you planning with that spade?" Hartley called out, his voice carrying the authority of a man whose building expertise was respected throughout the community. He stepped carefully across the threshold, noting the precision of Dixon's foundation work while remaining baffled by this latest development. Dixon looked up from his measuring, his weathered face revealing neither embarrassment nor defensiveness. At 42, he had learned to choose his battles carefully, especially when it came to explaining techniques that seemed to contradict accepted practice. "Digging a drainage channel, Samuel, 6 inches wide, 4 inches deep, all the way around." The explanation did nothing to reduce Hartley's confusion. In his experience, water problems were addressed by building properly in the first place, tight chinking, good roof construction, and adequate foundation height. The idea of planning for water to get inside suggested a fundamental misunderstanding of cabin construction principles. "Water don't get inside if you build right the first time," he said, his tone carrying the patience of a teacher correcting a student's misconception. But Dixon had already begun digging, his spade cutting through the packed earth with the steady rhythm of a man who had made up his mind. The trench took shape slowly, following the interior perimeter with mathematical precision. 6 inches from the wall, exactly 4 inches deep, sloping gently toward what would become the exit point near the door. As the morning progressed, other neighbors found excuses to stop by, drawn by curiosity about Dixon's unusual approach to floor installation. The Morrison brothers arrived just after noon, ostensibly to borrow Dixon's froe, but clearly more interested in understanding what they were witnessing. James Morrison, the older of the two, had considerable carpentry experience and prided himself on efficient construction methods. The sight of Dixon carefully removing individual spadefuls of dirt from inside a nearly completed cabin seemed to violate every principle of practical building. "Never seen anything like this, Robert," Morrison said, watching Dixon work. "What's your grandfather's old country methods got to do with mountain cabin building?" The question carried an edge of skepticism that reflected the community's general attitude toward techniques that seemed to ignore local wisdom. Dixon paused in his digging, wiping sweat from his forehead with the back of his hand. His grandfather Johann had indeed come from the old country, bringing with him construction methods developed over centuries of managing moisture in regions where timber buildings faced constant challenges from rain and snow. But explaining that heritage to neighbors who viewed efficiency as the highest virtue seemed likely to generate more questions than understanding. "Johann always said water finds a way," Dixon replied simply, returning to his careful excavation. "Better to give it a path you choose than let it pick its own." The philosophy behind the statement was rooted in decades of observation and experience, but to his neighbors it sounded like unnecessary caution applied to a problem that proper construction should prevent entirely. By afternoon, the community consensus had solidified around the idea that Dixon was overthinking a simple process. Hartley expressed what everyone was thinking when he observed that Dixon had already spent more time on his drainage trench than most men spent on their entire floor installation. The mathematics seemed to support the criticism. 16 hours of careful digging and stone laying for a system that addressed a problem most builders never encountered. But Dixon continued his methodical work, lining the completed trench with carefully selected river stones, each one chosen for size and shape to create a channel that would carry water efficiently toward the exterior drain. The stones, gathered over several trips to the creek below, ranged from 1 to 3 inches in diameter, sized to allow water flow while preventing clogging from debris. Sand filled the gaps between stones, creating a stable base that would maintain proper drainage slope over time. As evening approached and Dixon fitted the final stones into place, the completed drainage system represented a level of preparation that seemed excessive to everyone who had witnessed its construction. The interior trench connected seamlessly to the exterior drain, a hollowed basswood log that would carry water well away from the foundation. The entire system demonstrated engineering principles that most frontier builders never considered, based on the assumption that such elaborate precautions were unnecessary for properly constructed cabins. The community judgment was swift and unanimous. Dixon had wasted 2 days solving a problem that didn't exist, using methods that complicated simple construction unnecessarily. But as he prepared to install his floor joists over the completed drainage system, Robert Dixon understood something his neighbors had not yet learned: the difference between building for normal conditions and building for the inevitable exceptions that tested every structure's weaknesses. Time would reveal which approach proved wiser, though the lessons would come at a cost his neighbors could not yet imagine. The science behind what Dixon understood and his neighbors dismissed lay hidden in processes they could not see but would eventually experience in devastating detail. Water possessed an almost supernatural ability to find weaknesses in even the most carefully constructed buildings, exploiting microscopic gaps and following paths that defied common sense. The stone foundations that supported every cabin in Watauga County, massive and seemingly impervious, actually functioned as giant wicks that drew moisture upward through capillary action into the wooden sill logs that rested directly upon them. The process began invisibly, with humidity levels that felt normal to human occupants, but created perfect conditions for the decay fungi that lay dormant in every piece of timber. When moisture content in wood reached 18% or higher and remained there for extended periods, these microscopic organisms awakened and began their patient work of breaking down cellulose and lignin, the very substances that gave wood its strength. The sill logs, positioned at the critical junction between stone and timber, bore the full weight of walls and roof while simultaneously serving as the primary pathway for moisture moving from foundation to frame. Even the most perfectly constructed cabin faced inevitable water intrusion from sources that frontier builders understood but consistently underestimated. Roof leaks developed as logs settled and shrank during their first year in place, creating gaps that no amount of initial chinking could permanently seal. The mud and moss mixture that filled spaces between logs worked well for the first season, but temperature changes caused it to crack and fall away in small pieces that left openings for wind-driven rain. Each cooking fire and oil lamp added moisture to the interior air, which condensed on cold walls during winter months and trickled down to collect at floor level. The most insidious water source came from below, where rain bouncing off stone foundations created splash patterns that drove moisture into the tiny gaps where sill logs met stone. Even a perfect fit between timber and foundation still allowed microscopic channels for water to penetrate, especially as the logs aged and developed the hairline cracks that appeared in all seasoned wood. Spring snowmelt brought additional challenges, as soil saturation forced groundwater upward through foundation stones, while seasonal flooding tested every seal with sustained moisture pressure. Most builders addressed these challenges through hope rather than engineering. They assumed that careful initial construction would prevent problems, that their chinking would hold indefinitely, and that minor water intrusion represented acceptable normal conditions rather than the beginning of structural disaster. When leaks appeared, they responded with patches and repairs, treating symptoms while ignoring the underlying reality that moisture would always find new pathways into buildings that lacked comprehensive water management systems. The conventional approach required living with dampness as an unavoidable aspect of frontier life. Families accepted wet floors after heavy storms, musty odors that indicated hidden moisture problems, and the gradual appearance of water stains that marked the slow progress of building decay. They developed elaborate indoor drying routines for dealing with clothes and bedding that never quite stayed dry, and they learned to position furniture away from walls where condensation created perpetually damp conditions. Dixon's engineering approach reversed this entire philosophy by acknowledging that water intrusion was inevitable and planning accordingly. His stone-lined trench provided an immediate destination for any moisture that entered the cabin through the dozens of pathways that would develop over time. Rather than hoping to keep water out, he had created a system that assumed water would get in and gave it a controlled path to escape before it could begin the destructive work of rot. The technical specifications of his drainage system reflected decades of accumulated wisdom about water behavior and building science. The 6-inch width provided adequate flow capacity for even heavy water intrusion while remaining narrow enough to install without compromising floor strength. The 4-inch depth ensured that water would move by gravity toward the exit drain while staying below the level of floor joists. The 2-inch slope built into the trench bottom created sufficient hydraulic gradient to prevent standing water anywhere in the system. Most critically, the continuous perimeter coverage meant that moisture entering the cabin at any point would encounter the drainage system rather than pooling against sill logs or soaking into subflooring. The stone lining prevented the trench itself from becoming a source of moisture problems while creating a permanent channel that would function effectively for decades without maintenance beyond annual cleaning. The first test of these competing philosophies came with the summer thunderstorms of 1879. Mountain weather patterns brought intense rainfall events that could dump several inches of water in a few hours, creating conditions that challenged every aspect of cabin construction. While Dixon's neighbors scrambled to position buckets under new leaks and mop up water that seeped through foundation joints, his drainage system quietly performed its intended function. Water that found its way past his chinking flowed immediately into the stone-lined channel and disappeared through the exterior drain, leaving his floors dry and his sill logs protected from the moisture that was beginning its destructive work on neighboring buildings. The trench collected not just obvious leaks, but also the subtle seepage that other cabins absorbed into their wooden structures, the condensation that ran down interior walls, the minor foundation infiltration that seemed insignificant, and the humidity-driven moisture that accumulated in enclosed spaces. By autumn, the first season's results provided clear evidence of the different approaches' effectiveness. Dixon's cabin showed no water stains, no musty odors, and no signs of the moisture damage that was already becoming visible in buildings constructed using conventional methods. His neighbors' cabins revealed the telltale indicators of water problems: discolored floorboards near walls, occasional puddles after storms, and the subtle but unmistakable smell of dampness that indicated moisture was accumulating faster than it could naturally evaporate. The community reaction remained dismissive, attributing Dixon's dry conditions to luck rather than superior engineering. They convinced themselves that his elaborate preparations had been unnecessary, that the problems they were experiencing represented normal settling issues that would resolve themselves as their buildings aged. The mathematical reality suggested otherwise. Dixon had invested 36 hours total in creating a system that would protect his cabin indefinitely, while his neighbors were already spending additional hours each month managing moisture problems that would only worsen with time. But the true test lay ahead, in weather patterns that would challenge every building technique and reveal which approach could withstand conditions that exceeded normal expectations. The wet years were coming, and with them would come the definitive proof of which building philosophy could protect families when nature tested the limits of frontier construction methods. The weather patterns that arrived in 1880 defied every prediction based on local memory and traditional seasonal expectations. Spring rains began in February and continued with relentless persistence through what should have been the dry months of summer, creating conditions that transformed routine cabin maintenance into desperate struggles for structural survival. The Watauga River, normally a manageable waterway that provided power for grist mills and transportation for timber, swelled to levels that old-timers claimed exceeded anything in their lifetimes. Rainfall measurements, carefully recorded by the county clerk who maintained weather data for agricultural planning, revealed the mathematical scope of the challenge facing every building in the region. 1880 brought 43% more precipitation than the previous decade's average, with individual storm events delivering 3 to 4 inches of rain in single afternoons. The saturated ground could no longer absorb the continuous moisture input, creating surface runoff that overwhelmed drainage systems and forced water into every vulnerable point in human construction. Samuel Hartley's cabin, completed just 2 years earlier, using methods that had served him successfully for over a decade, began showing the first subtle signs of moisture stress during the late spring flooding. Water stains appeared on floorboards near the north wall, where prevailing storms drove rain against the foundation with particular intensity. The discoloration seemed minor at first, just slight darkening of wood grain that could be attributed to normal humidity fluctuations. But the pattern persisted and expanded, indicating that moisture was penetrating the building envelope and accumulating faster than natural evaporation could remove it. The technical reality behind these visible symptoms involved processes that occurred below the threshold of human awareness, but would determine whether buildings survived or failed over the coming years. Hartley's sill logs, resting directly on stone foundations according to standard frontier practice, absorbed moisture through direct capillary contact and began the slow transformation from structural timber to weakened, partially rotted wood. The moisture content in these critical load-bearing members rose from the normal 12 to 15% range to the dangerous 18 to 20% levels that supported active fungal decay. James Morrison's cabin faced even more severe challenges due to its position in a slight depression that concentrated runoff from the surrounding hillside. By midsummer of 1880, persistent puddles formed under his kitchen area after every significant rain event, creating ideal conditions for the accelerated decay that threatened buildings exposed to standing water. Morrison found himself spending hours each week mopping up intrusions and repositioning furniture to avoid the dampest areas, But these reactive measures addressed symptoms while the underlying structural damage progressed invisibly. The Morrison family's daily routine adapted around their building's moisture problems in ways that revealed the true cost of inadequate water management. Cooking activities moved away from the north wall, where condensation created perpetually damp conditions. Sleeping arrangements shifted to avoid areas where humidity concentrated during cool nights. Food storage required constant vigilance to prevent spoilage in spaces that never quite dried completely. The cabin remained habitable, but at the cost of comfort and convenience that undermined the very purpose of permanent shelter. By 1881, the mathematical progression of structural damage became undeniable in multiple buildings throughout the community. The Miller family's cabin developed a visible sag in the north wall where the sill log had lost enough structural integrity to compress under the building's weight. What began as moisture intrusion had evolved into engineering failure that threatened the stability of the entire structure. The Millers faced a choice between expensive repairs that would require jacking up walls and replacing damaged timbers, or accepting progressive deterioration that would eventually make their home uninhabitable. Dixon's cabin, meanwhile, demonstrated the effectiveness of preventive water management under conditions that exceeded every reasonable expectation. His stone-lined drainage system handled the unprecedented moisture loads with mechanical efficiency that validated his grandfather's engineering principles. During the heaviest storm events, neighbors could observe water flowing through his exterior drain at rates that reached 4 to 5 gallons per hour, clear evidence that significant amounts of moisture were entering his building, but finding immediate pathways for removal rather than accumulating in structural components. The performance metrics of Dixon's system provided quantifiable proof of superior engineering during the most challenging conditions. His drainage trench maintained proper flow characteristics even when debris from interior activities occasionally accumulated in the channel. The 2-inch slope gradient ensured that temporary blockages cleared themselves as water levels rose, while the stone lining prevented erosion that would have compromised earth-lined channels. Annual maintenance required only the removal of accumulated leaves and dust, a 2-hour task that preserved system functionality indefinitely. More importantly, structural assessments of Dixon's cabin revealed no signs of the moisture damage that was becoming epidemic in conventionally constructed buildings. His sill logs remained at normal moisture content levels, showing no evidence of the softening and discoloration that indicated fungal attack. His interior floors stayed solid and stable, without the springiness that developed when subflooring began to rot. The absence of musty odors confirmed that his building was successfully managing moisture rather than merely tolerating its accumulation. The social dynamics within the community began shifting as the evidence mounted that Dixon's elaborate preparations had addressed real rather than imaginary problems. Conversations at the general store and after church services increasingly focused on building maintenance issues that seemed to affect everyone except the man who had been mocked for overthinking simple construction. The contrast became impossible to ignore when families gathered for community events and inevitably discussed the ongoing challenges of keeping their homes dry and structurally sound. The summer of 1882 brought the crisis to its peak with weather patterns that local residents would remember as the 40-day rain, a period of continuous precipitation that tested every aspect of frontier engineering. Streams became torrents, roads became impassable, and buildings faced moisture stress that exceeded anything in regional memory. The accumulated damage from 3 years of abnormal weather conditions reached the threshold where minor problems became major failures. 7 cabins in the immediate community showed serious structural compromises that required immediate attention to prevent collapse. Emergency measures included exterior trenching projects that attempted to divert surface water away from foundations, but these reactive solutions came too late to prevent the damage that years of moisture accumulation had already inflicted. The community faced a crisis of shelter security that threatened the fundamental viability of their settlement. Throughout this escalating disaster, Dixon's cabin remained completely functional, its occupants dry and comfortable while their neighbors struggled with increasingly desperate conditions. The vindication of his methods was no longer a matter of theory or debate. It was demonstrated daily by the simple fact that his family continued their normal routine while others reorganized their lives around building failures. The man who had been dismissed as wastefully cautious was quietly emerging as the only person in the community who had correctly anticipated and prepared for the challenges that frontier construction would inevitably face. Winter 1883 arrived with unusual severity, bringing temperatures that remained below freezing for weeks at a time and testing every structural weakness that 3 years of excessive moisture had created in the community's buildings. The freeze-thaw cycles that characterize Appalachian winters normally caused minor settlement and adjustment in log construction, but cabins already compromised by water damage faced catastrophic failures when expanding ice completed the destruction that fungi had begun. Samuel Hartley discovered the extent of his building's deterioration on a bitter February morning when the distinctive sound of cracking timber jolted him awake before dawn. The north sill log of his cabin, weakened by years of moisture absorption and fungal decay, had finally surrendered to the combined stresses of structural loading and thermal expansion. The 18-inch white oak timber that had seemed solid when installed now compressed and split under the weight it could no longer support, allowing the entire north wall to sag inward by nearly 4 inches. The engineering nightmare that confronted Hartley represented every frontier builder's worst fear, a structural failure that threatened the integrity of his entire shelter during the season when rebuilding was impossible. The sagging wall pulled floor joists out of alignment, opened gaps in the chinking that allowed bitter wind to penetrate the interior, and created a cascade of secondary problems that made the cabin increasingly uninhabitable. Emergency repairs using temporary props and bracing provided minimal stability while Hartley contemplated the massive undertaking required to restore his home's structural soundness. The sill log replacement process demanded resources and expertise that tested the limits of frontier construction capabilities. The first challenge involved removing interior flooring to access the damaged foundation interface, while the family continued to occupy the building during mountain winter conditions. Each floorboard had to be carefully pried up and set aside for reinstallation, exposing the subflooring and joist system that would need temporary support during the repair work. The precision required to avoid further structural damage while accessing the failed component demanded skills that few builders possessed. Installing the temporary jacking system represented the most dangerous phase of the entire operation. The wall structure, weighing over 2,000 pounds of logs, chinking, and roofing materials, had to be lifted gradually and supported by an arrangement of wooden posts and stone piers that could hold the massive load while the damaged sill log was removed and replaced. One miscalculation or equipment failure could result in complete wall collapse, destroying months of work and potentially injuring anyone working inside the building. The actual removal of the rotted sill log revealed the full extent of moisture damage that had accumulated over 3 years of inadequate water management. What appeared to be solid 18-inch timber from the exterior showed extensive internal decay that had reduced its load-bearing capacity to a fraction of the original strength. The wood crumbled in sections, releasing the distinctive musty odor of advanced rot and exposing the network of fungal threads that had systematically destroyed the timber's structural integrity from within. Selecting and installing the replacement sill log required starting the entire construction process over again at the foundation level. The new timber, cut from standing dead chestnut to ensure proper seasoning, had to be precisely notched and fitted to mate with the existing wall structure while sitting perfectly level on the stone foundation. Every joint required careful adjustment to maintain the building's structural geometry while accommodating the settling and movement that had occurred during the failure and repair process. The labor requirements for Hartley's sill log replacement consumed 3 weeks of intensive work by 5 experienced men, representing over 200 hours of skilled construction time. The material costs included not only the replacement timber, but also the temporary supports, additional chinking materials, and specialized tools required for the complex operation. Most critically, the work had to be completed during winter conditions that made every aspect of construction more difficult and dangerous. Morrison's cabin faced similar challenges during the spring of 1884, when his kitchen area sill log failed under conditions that made repair work only slightly less hazardous than winter operations. The location of the damage required removing cook stove and chimney components to access the failed structural member, disrupting the family's ability to prepare food during the lengthy repair process. The accumulated cost in labor, materials, and lost domestic productivity represented a devastating financial burden for a frontier family operating with minimal cash resources. The Miller family confronted an even more complex situation when foundation settling, caused by softened sill logs that could no longer maintain proper contact with stone supports, created multiple structural problems that cascaded throughout their building. The repair work required not only sill log replacement, but also releveling of the entire foundation system and reconstruction of wall sections that had moved out of alignment. The scope of necessary work approached the labor investment required to build an entirely new cabin. The most tragic example of structural failure's human cost appeared in the case of the widow Thompson, whose husband had built their cabin using standard methods before his death in 1882. Elizabeth Thompson lacked both the financial resources and technical knowledge required to address the sill log deterioration that made her home increasingly dangerous and uncomfortable. The cabin's progressive failure forced her to abandon sections of the building as they became uninhabitable, concentrating her family's activities in the remaining structurally sound areas. By fall of 1884, the mathematical reality of conventional construction methods had been demonstrated with devastating clarity. The average cabin in the community required major structural repairs every 8 to 12 years, consuming between 150 and 200 hours of skilled labor plus materials, costs that represented substantial percentages of frontier families' annual cash incomes. The ongoing maintenance requirements created a cycle of construction work that diverted resources from agricultural activities and other productive pursuits. Dixon's cabin provided a stark contrast to the community's mounting structural failures. His original sill logs showed no signs of moisture damage, settling, or decay after 5 years of service under conditions that had destroyed similar components in neighboring buildings. The stone-lined drainage system continued to function exactly as designed, removing moisture before it could begin the destructive processes that required such expensive repairs in conventionally constructed cabins. The structural assessment of Dixon's building revealed foundation contact that remained perfect, with no settling, gaps, or misalignment between timber and stone components. His interior conditions stayed consistently dry and comfortable without the musty odors, water stains, or springy floors that indicated hidden moisture damage. The maintenance record for his cabin consisted entirely of the annual 2-hour cleaning of his drainage channel, a minimal investment that preserved the system's effectiveness indefinitely. The community's awakening to the value of Dixon's methods came gradually as the evidence accumulated beyond any possibility of denial. The man who had been mocked for wasteful preparation was the only builder whose home remained structurally sound, while others faced reconstruction projects that consumed months of labor and hundreds of dollars in materials. His 2 days of initial trench digging had prevented decades of expensive repairs while providing his family with security and comfort that conventional methods could not match. The social dynamics shifted decisively when neighbors began asking Dixon to explain exactly how his drainage system worked and whether similar installations could be retrofitted into existing buildings. The community fool had quietly become the local expert whose engineering approach offered the only proven solution to problems that threatened everyone's long-term shelter security. The transformation of community attitudes toward Dixon's methods began quietly in 1885 when 3 neighbors independently decided to incorporate interior drainage systems into their new cabin construction projects. The Morrison brothers, planning a replacement for their flood-damaged original home, were the first to openly request detailed instructions about trench installation and stone lining techniques. Their decision marked the beginning of a fundamental shift from mockery to adoption that would reshape building practices throughout the region. James Morrison's approach to implementing Dixon's drainage concept demonstrated the practical intelligence that allowed superior techniques to spread among frontier builders who valued results over rigid adherence to tradition. During his cabin's foundation phase, Morrison carefully observed Dixon's original installation, taking mental notes about trench dimensions, stone selection criteria, and drainage slope calculations. The retrofit of his system during sill log replacement work provided an ideal opportunity to test the method's effectiveness under challenging conditions. The technical refinements that emerged as Dixon's technique spread through the community reflected the collaborative nature of frontier engineering development. Local builders discovered that different types of available stone worked better for specific applications: flat creek stones for trench lining, rounded river rocks for French drain applications, and angular quarried stone for areas requiring maximum structural stability. The regional variations in soil composition and drainage patterns led to modifications in trench depth and slope gradients that improved system performance under local conditions. Samuel Hartley's conversion to Dixon's methods represented the most significant endorsement possible within the community's informal technical hierarchy. During his extensive sill log replacement project in 1885, Hartley made the decision to install a complete interior drainage system rather than simply repair the existing conventional foundation interface. The choice required additional labor and materials at a time when he was already facing substantial reconstruction costs, but Hartley had experienced firsthand the consequences of inadequate moisture management. The installation of Hartley's drainage system provided the community with a detailed demonstration of techniques that had previously been visible only in Dixon's original cabin. Neighbors gathered to observe the trench excavation process, stone selection methods, and the precise fitting work required to connect interior channels with exterior drainage components. Dixon's willingness to share his knowledge without claiming proprietary ownership of the techniques earned him respect that transcended his vindication on technical grounds. The measurable results from early adopters provided quantifiable evidence of the drainage system's effectiveness under real-world conditions. Morrison's retrofitted cabin showed immediate improvement in moisture control, with standing water problems eliminated and interior humidity levels stabilized within acceptable ranges. Hartley's new installation prevented the recurrence of sill log deterioration that had plagued his previous construction, demonstrating that the technique could protect buildings from the ground up when properly implemented. By 1888, 12 cabins in Watauga County incorporated some variation of Dixon's interior drainage concept, creating a substantial sample size for evaluating long-term performance characteristics. The adopter buildings consistently showed extended sill log lifespans that approached 20 to 25 years compared to the 8 to 12-year replacement cycles common in conventional construction. The financial implications of this improvement represented hundreds of dollars in avoided repair costs over the lifetime of each building. The techniques spread beyond Watauga County occurred through the informal networks that connected mountain communities throughout the Appalachian region. Traveling craftsmen, itinerant preachers, and traders carried knowledge of Dixon's drainage methods into neighboring counties in Tennessee and Virginia, where similar moisture problems plagued frontier construction. Each successful implementation provided demonstration sites that encouraged further adoption and regional adaptation of the basic engineering principles. Local carpenter William Hayes began maintaining detailed notes on what he termed Dixon's drain method as part of his effort to codify building techniques that proved superior to traditional approaches. Hayes's documentation provided the first systematic analysis of installation procedures, material requirements, and performance expectations for interior drainage systems. His records would later serve as the foundation for written construction guides that preserved and transmitted the technique to future generations of builders. The technical evolution of the drainage concept continued as builders gained experience with installation and maintenance procedures. Specialized tools developed for trench excavation included narrow spades designed for working in confined spaces, and stone bars for precise placement of drainage materials. Local blacksmiths began producing standardized drain pipes and connection fittings that improved system reliability while reducing installation time and complexity. The broader cultural impact of Dixon's Vindication extended beyond technical building improvements to influence community attitudes toward innovation and traditional knowledge preservation. The recognition that old country techniques could provide solutions to New World problems encouraged other settlers to examine their ancestral building practices for applicable wisdom. The collaboration between traditional European methods and frontier adaptation became a model for technical development that honored both heritage and practical necessity. Regional building practices evolved to incorporate moisture management as a fundamental design consideration rather than an afterthought addressed during problem-solving phases. New construction projects routinely included foundation drainage planning from the initial site selection through final installation procedures. The preventive approach to water control became standard practice that influenced everything from cabin positioning to material selection and construction sequencing. The long-term validation of Dixon's approach emerged through comparative analysis of building performance over multiple decades. His original cabin remained on its initial sill logs through 1909, 30 years after construction, while conventional buildings in the community averaged 2 to 3 sill log replacement cycles during the same period. The cumulative maintenance cost differential represented hundreds of dollars per building, demonstrating that Dixon's 2-day investment had generated enormous long-term value. The mathematical vindication of preventive engineering became undeniable when analyzed over complete building life cycles. Dixon's initial 36 hours of drainage system installation and maintenance work compared favorably to the hundreds of hours his neighbors spent on structural repairs and rebuilding projects. The $5 material investment in stones and installation time prevented repair costs that averaged $150 per major structural failure. By 1910, when Dixon reached 73 years of age, his drainage method had become sufficiently established throughout the region that young builders learned the technique as standard practice rather than innovative adaptation. The transformation from community mockery to accepted wisdom demonstrated the power of practical results to overcome initial skepticism and establish the foundation for building science principles that would influence construction practices for generations. The legacy of Dixon's work extended far beyond his original problem-solving efforts to establish moisture control as a critical component of durable building design. Modern construction codes requiring foundation drainage and moisture barriers traced their technical ancestry directly to the engineering principles that one Appalachian mountaineer had preserved from his grandfather's old country wisdom and validated through frontier necessity. The recognition that water management represented the difference between successful and failed construction became a fundamental tenet of building science that honored both traditional knowledge and practical innovation.